Bismillah, Alhamdulillah, wassalatu wassalamu ala Rasulillah. This is the second part of section 11.4, comparison tests, and it's about the limit comparison test. We studied the direct comparison test in the previous video, and we use the direct comparison test when we can prove easily that AN is less than convergent, series is less than convergent, or greater than divergent. So if the terms are larger than the terms of a convergent series or smaller than those of divergent series, in these cases, the direct comparison test does not apply. So less than convergent is okay, but if it is larger than convergent, then we cannot use the direct comparison test. Or smaller than divergent, we cannot use the direct comparison test. For example, this series, summation 1 over 2 to the power n minus 1. Now, this is the relation between 1 over 2 to the power n minus 1 and 1 over 2 to the power n, because we said that 1 over 4 minus 1, for example, is greater than 1 over 4 because we are subtracting 1 here. So you cannot say that this is less than, it is not less than, it's greater than 1 over 2 to the power n. And 1 over 2 to the power n is a geometric series with r less than 1, so this is convergent. So this series, or the terms of this series, are larger than the terms of a convergent series. Doesn't help. I cannot use the direct comparison test because the direct comparison test says that less than convergent, not greater than convergent. So what to do? I know that I can compare this series with 1 over 2 to the power n, but how to prove that this series is convergent? So here comes the limit comparison test. We also have two series with positive terms, so the same condition as the direct comparison test, but here we will prove that summation an is convergent by or divergent by taking the limit of an over bn when n approaches infinity. And if this limit is a positive number greater than zero, a positive real number, finite number, not infinity, positive real number. So either both series converge or both series diverge. So this is the limit comparison test. You take an and bn, you divide them, and you find the limit when n goes to infinity. If it's a positive real number, then both series converge or both series diverge. For example, this series, test the series. Well, we know that this is an. And what is bn? We know how to find bn. It is 1 over 2 to the power n. We take the highest power here and there, or the term that's really uh, controls the situation when n goes to infinity. So what is this? What is bn? We know that bn summation 1 over 2 to the power n is a convergent geometric series since r is 1 over 2 less than 1. So, and I cannot show that an is less than bn using the direct comparison test. So let me find an over bn. Well, this would be 1 over 2 to the power n minus 1 divided by 1 over 2 to the power n. So it would be 1 over 2 to the power n minus 1 multiplied by 2 to the power n. This is how we divide two fractions. So we will have 2 to the power n over 2 to the power n minus 1. So this is an over bn. And let us now find the limit of 2 to the power n over 2 to the power n minus 1 when n goes to infinity. I can take 2 to the power n over 2 to the power n, I can say it is immediately 1. Or if you like, I can multiply by 2 to the power negative n over 2 to the power negative n. Then if you multiply here, you get 2 to the power 0, which is 1. And here you get 2 to the power 0, which is 1, minus 1 over 2 to the power n. Now, if you replace n with infinity, 2 to the power infinity, infinity, 1 over infinity is 0. So I'll get 1 over 1, which is 1. Now, 1 is greater than 0. So by limit comparison test, summation an also converges. Because summation bn converges, so summation an converges. Determine whether this series converges or diverges. If you have plus up and plus down, positive up and down addition, it is not the using of direct comparison test is not possible in this case. You notice that if you have 3 minus 1 over 4 plus 5, for example, minus up and plus down, you can write it less than 3 over 4 plus 5, and then you can write it less than 3 over 4. So you can get rid of the negative and the positive. And also, if you have 3 plus 4 over 5 minus 1, positive up and negative down, you can write it greater than 3 over 5 minus 1, and then greater than 3 over 5. But if you have positive, positive, or negative, negative, there is no way to do it like this. So we need to determine Bn and to use the limit comparison test. Also make sure that you pay attention to An, that An is positive, is greater than 0 for all n greater than or equal to 1. So it's positive terms. Also here, if you replace n by 1, it would be positive. So An here is positive for all n greater than or equal to 1. That's the condition of the limit comparison test. What is Pn? The term with the largest power is 2n squared, and here I have square root of n to the power 5. This would be n to the power 5 over 2, and it would be 2 over n to the power half. 5 over 2 minus 2. So this is, what is this? Well, summation 1 over n to the power half is a divergent P series because B equals to half less than 1. So 2 over n to the power half would be a multiple of a divergent B series. So it would be also divergent. So now let us find an over bn. When you divide an over bn, now this is bn, okay? This is bn. When you let us take it 1 even. There is no need to take 2. Okay, we can just take it 1. Or you can take it 2, it's no problem. So I can divide an by bn. When we divide an by bn, what would happen always? This n to the power half would be in the numerator of an. So actually, let us do it again for one time. And then after that, I will do it quickly. So it is, we have this one divided by 1 over square root of n, or n to the power half. So it would be multiplied by square root of n over 1. So when we divide by bn, always what is in the denominator of bn will be multiplied by the numerator of en. So we will have 2 times n to the power 2 plus half, and 3 times n to the power 1 plus half. And here we have this one. Now, when I find the limit of an over bn when n approaches infinity, when n approaches infinity, we deal with the term with the highest power. So I have 2 n to the power 5 over 2, and here n to the power 5 over 2, square root of n to the power 5. So this, the limit would be 2, and 2 is greater than 0. So by limit comparison test, summation an also diverges, because summation bn is divergent. So summation an would be divergent because the limit of an over bn is greater than 0. This is how we choose uh, bn. Okay, this is how we choose bn. We keep the highest powers in the numerator and in the denominator. Use the limit comparison test to show that the first series converges. This series. Well, this series is a convergent P series because P is 2 greater than 1. So let us find the limit of an over bn when n approaches infinity. This is an and this is bn. If you multiply, if you find the limit, if you divide, sorry, an over bn, n square will be multiplied by n. So I'll have n cube here and here n cube minus 5. And when n approaches infinity, we deal with n cube up and n cube down. And this is 1 and this is greater than 0. So by limit comparison test, summation an also converges. So this is how we use the limit comparison test. Use the limit comparison test to show that the first series diverges here, comparing to the second one. Well, this is the harmonic series. It's also a P series where B greater than 1, so it is divergent. We know that. And this is Bn and this is An. You notice that I have minus and plus. I can use the comparison test here. Uh, can I? Minus and plus, let me see. Minus and plus, I can make it less than, not greater than. Plus and minus, I can make it greater than. Okay. So I cannot use the comparison. So let me find limits an over bn when n approaches infinity. Well, bn is 1 over n. So this n will be in the numerator of an. So I'll have n cube minus n square over n cube plus 2. And when we take the limit, we deal with the highest powers. So the limit is 1 greater than 0. So by limit comparison test, summation an also diverges. Determine whether this series is convergent or divergent. When I have plus here, I can make it less than. So we know that 1 over 3 plus 4 is less than 1 over 3. So I can say that 1 over square root of n square plus 1 is less than 1 over square root of n square, but this is n, so it doesn't help me because 1 over n is divergent. Less than divergent does not help to use the comparison test, the direct comparison test. So I have to use the limit comparison test here. And let me first say that an is greater than 0 for all n greater than or equal to 1. And it is always in any problem we have to say this, okay? first. Then let us determine Bn. Well, Bn is 1 over n, 1 over square root of n squared, which is 1 over n. And this is divergent. Well, the series is divergent, so it's better to write summation 1 over n is divergent, and the reason it is the harmonic series. And it is known that the harmonic series is divergent. Now, what is limit an over bn when n goes to infinity? This n will be multiplied in the numerator of an. And we have here square root of n squared plus 1. This is the highest power here, and the highest power here is this one. And notice that square root of n squared could be positive or negative, but n is positive. It starts from 1. So the limit is 1 greater than 0. So by limit comparison test, summation an also diverges because, of course, this is an, because summation 1 over n diverges. Well, here this is a plus than, I can make it less than, but it doesn't help because I need it greater than, because bn here is 1 over square root of n. And 1 over square root of n summation 1 over square root of n is a divergent B series. Because P is half less than 1. Of course, an are positive for all n greater than or equal to 1. So limit an over bn when n approaches infinity, and this is an, would be the limit of 2 square root of n when we divide an by bn. And this would be the limit of 2 square root of n over square root of n, and it would be 2 greater than 0. So by limit comparison test, summation an also diverges. You have plus and plus. Please do the same. Compare it with n over n cube, which is 1 over n square. Use limit comparison test to show that this series is convergent. Just similar statements. Here also bn is 1 over n square, and prove using limit comparison test that this series is convergent. Here bn is square root of n over n, so it's 1 over square root of n. So also use the limit comparison test to show that this series is divergent. Here bn is 2n over n to the power 4. You can't take n or 2n. So it's 1 over n cube, and it is a convergent P series. So use limit comparison test to show that summation an is also convergent. Let us do this one. When n goes to infinity, 3 to the power n will dominate the numerator because it's greater than n. much greater than n when n goes to infinity, also 2 to the power n. So I can take b to the power n here as 3 to the power n over 2 to the power n. Okay, and I can use limit comparison test. But I can use the direct comparison test here. But let me first say that an is positive for all n greater than or equal to 1. Now bn is 3 to the power n over 2 to the power n. So let me start by n plus 3 to the power n over n plus 2 to the power n. I know that 3 to the power n over 2 to the power n is a divergent geometric series because r is 3 over 2 greater than 1. So let me prove that this greater than this divergent series. I have plus in the numerator, so I can just write it greater than 3 to the power n over n plus 2 to the power n. Now I cannot say that this is greater than 3 over 2 all to the power n because this is a plus. But what can I say? I can increase the denominator. How can I increase the denominator? Replacing n by 2 to the power n, because n is less than 2 to the power n for n greater than or equal to 1. So this is equal to 3 to the power n over 2 times 2 to the power n. So it is half times 3 over 2 to the power n. Notice that summation 3 over 2 to the power n, or even if you multiply by half, is a multiple of a divergent geometric series because r is 3 over 2 greater than 1. And I proved that an is greater than bn, the terms are greater. So by direct comparison test, summation an also diverges. So this is another way, okay? You can replace n by 2 to the power n using this fact. Well, here I'll also do something. I'll start by e to the power n plus 1. This is an. If you look carefully to en, I have e to the power n plus 1 and e to the power n plus 1 here, but there is an n here. So I will compare it with 1 over n. I can say that this is greater than en plus 1 over n en plus n because 1 is less than n. So I'm increasing the denominator. So this is larger than this as a fraction. Of course, an is greater than 0 for all n greater than or equal to 1. If I realize that I have this one, so I can take n as a common factor from the denominator, and I can cancel this with this, I get 1 over n. So by this I show that an is greater than 1 over n, but summation 1 over n is divergent. It is the harmonic series. So by direct comparison test, summation an also diverges because I proved that an is greater than the terms of a divergent series. Bn here is 1 over n times square root of n square, which is n. So it's 1 over n square. I'll do this by the limit comparison test. So first notice that an when n is 1, when n is 2, I start from 2, is greater than 0 for all n greater than or equal to 2. And this is a convergent uh, summation. 1 over n square is a convergent p series. N is 2 greater than, p is 2 greater than 1, and limit an over bn when n approaches infinity is the limit of n square will become here up when n goes to infinity. We deal with terms with the highest power, and n is positive. It is 1 greater than 0. So by limit comparison test, summation an also converges. Well, here I have cosine square n. And we have seen that cosine square n is a number between 1 and 0. So when n goes to infinity, it doesn't do anything. It doesn't, it's not larger than 1 even when n goes to infinity. So Bn here would be n square over n cube or 1 over n. And summation 1 over n is divergent. It is the harmonic series. So I can say that n square plus cosine square n over n cube is greater than, because cosine square is greater than 0, positive. So I can say that this is greater than this, and this is 1 over n. So I can use the direct comparison test. It's greater than 1 over n. 1 over n, summation 1 over n is divergent. So summation an is divergent using the direct comparison test. Well, here 1 over e to the power n, 1 over e to the power, this is a geometric series. So if I take bn e to the power negative n, which is 1 over e to the power n, summation 1 over e to the power n is a convergent geometric series because r is 1 over e and it is less than 1. And if I take the limit of en over bn when n approaches infinity, this would be the limit of, this is an. This is an, sorry, over bn. Now these two cancels. And when I find the limit of this when n approaches infinity, 1 over infinity is 0. 1 plus 0 square is 1, and it's greater than 0. So by limit comparison test, summation an also converges. I hope by now you can distinguish between direct comparison test and limit comparison test. Have a nice time and study hard.